Alright, so today, as promised, we're going to be covering a new topic, which is free Lie algebras, which kind of isn't all that new. We've seen hints of it with the universal algebra, but we're going to study it in more detail here. And throughout this topic, throughout this whole chapter, which I will probably mention when the chapter's over, we're going to have K be a commutative and associative ring with unit and all modules and algebras will be over K. Will be over K. So our first topic is actually one you don't see a lot. It's going to be free magmas. Keep in mind, a magma, I guess I'll go through the definition here. Maybe I should have not intended that at all. So, definition. So, a magma is a set M with a binary map. Maps, which is of course M and M into M, and we're going to write this as X and Y being sent to XY, is called a magma. And that's it. There's no structure of any kind on this product. It's just like, other than closure. Closure is the only assumption. You take two things from the set, you get another thing from the set. That's a magma. Pretty loose structure. Doesn't seem like there could be a lot we could say about a magma, but we go forward here. We'll let X be a set. We're going to inductively define Xn as follows. X1 is just going to be X, and then Xn is going to be the disjoint union. Keep in mind this is disjoint, so it means that we're keeping track of like where everything came from, even if two different covers of an item would normally go to the same in a union. This is like, yeah. And that's just the disjoint union of the products of XP and XQ for n at least 2. So essentially, items of Xn is a list of n items from X, but we keep track of like how we split it up. Like if we have n items, it is explicitly of the form like 1 through m, and m plus 1 through n, and then if like, even if all the items are the same, if we that split is in a different place, it's considered a different item. And this will make sense when we get to see what a free magma is exactly. Now we're going to put the magma of X, mx, to be the disjoint union. Doesn't really need to be disjoint, but it will anyways, of these xn from 1 to infinity. And define our map, our binary map on mx, which is going to be mx and mx to mx, as xp. First item is going to be from some xp, and the second is going to be from some xq. And that's going to be sending them into xp plus q through this process I showed above, which is of course still in our mx. And yeah, this second, I guess you can get this xp times xq into xp plus q more formally from our second condition here with the disjoint union. So then this mx is the free magma on X. An element W and mx is called a non-associative word. On X with a length L of W being the n such that W is in mx through some xn. So essentially it's how many elements are in W. Theorem. Let n be a magma and f of x to n a map. Then there exists a unique f from the free magma of x to n, which is going to be a magma homomorphism. So this is, as always, just going to take our product is going to be essentially kind of commute with this f. And this is going to be extending our original map. And our proof is just going to let f of u times v equal to f of u times f of v inductively. So essentially we can just because on the structure of x1, which is just x, capital F is equal to lowercase f by definition. And then every w with length greater than 1 is the product of two smaller xn's, elements of xn, and so you can just repeat that until you get down to the case of length of 1. And we will note that of x is generated by x, and that m is an element of the free magma of x and outside of just the original x, if and only if m equals uv for unique u and v. And essentially, if we have this 1 through n as before, there's internal brackets, so there's only one way to split it up, essentially. So now we're going to take we're going to tie this to the free algebra on x. We're going to let ax be the K algebra, where K is our base ring, of our free magma mx. Then each element alpha in ax is a finite sum alpha is the sum of CMM with M in our magma and CM in our base ring. And the multiplication in AX extends to multiplication of MX. So I'm thinking it's an algebra, the sum of two elements of AX is just summing them up component-wise, where the components are listed by the elements of the free magma on X. And multiplication-wise, I believe we just multiply the, pairwise, we multiply the ring components of each component, and also we multiply their indices, which are elements of the free magma, with the magma product. I believe. I'm not 100% sure on that, but in this case we say that AX is the free algebra on X. And, well, how do we know it is the free algebra? It essentially means any other algebra on X. I believe any map to another algebra on X factors from X factors through this, which we will see here. We will let B be a K-algebra and F be just a map from X to B. And there exists a unique capital F from AX to B, which is a K-algebra homomorphism which extends F. Yeah, so every map from our X to B filters through as the canonical injection from X to AX, and then our new F from AX to B. We saw before we can extend F to a magma homomorphism. F prime from MX to B, which extends F. Yeah, we already have that. With B as a magma. By linearity, we extend this map to a K-linear map F from AX to B and that's basically the idea. We get it's a homomorphism from our previous results plus the fact that the map from MX to AX is gonna behave well with that. And it's unique because our first extension is unique from our previous result, and then we're just extending it linearly. So there's only one way to do that. This is my explanations are kind of rough here, I'm sorry, but I know what I'm talking about. This is ultimately for me, and I know what I'm saying. Now we note that AX is a graded algebra. With the homogeneous elements of degree n being linear combinations of words of length n. Keeping in mind that our algebra is essentially pairing together every possible element of our magma with a weight essentially from K. Now, how do we turn this into a Lie algebra? free Lie algebra on X. We're going to let I be the, remember this routine? It's the two-sided ideal. Of AX generated by the eighth product of elements A with themselves for A in X, and elements of the form J, A, B, C, where JABC is equal to ABC plus CAB, as you would expect. Then we're going to set LX to be equal to AX over I. This is the free Lie algebra on X. Okay. Proposition. We'll go right into the components of this proposition. First off, for arbitrary f from our generating set X to some X prime, there exists a unique capital F from LX to LX prime. Keep in mind this capital X also does not have any special properties. It's not a homomorphism of Lie algebras or anything, such that our unique condition is that the restriction of F to X inside of LX is just F. Keep in mind that X is X1 inside of MX, and therefore LX and AX, so it's elements of, it's words of length 1. And we see here our two generating elements for our I is AA, which has to have length of at least 2, and JABC, which has to have length of at least 3. So we're going to have a copy of X, essentially like X times 1 in our unit in our ring, and that's going to be like unperturbed, essentially. Okay. Okay, there is, I'm going to write this out. This is something I'm going to have to look up here too. Condition 2. If this is exactly how they write it, X alpha, comma, I alpha beta is a direct system. I don't know what that is. And X is the limit of x alpha, then Lx is the limit of Lx alpha. Three, get of course our good old friend change of base ring. If the ring K prime extends the ring K, then the change of base ring of our free Lie algebra is what you would expect, with the K tensor of our original Lx with K prime. Yeah. I, our two-sided ideal of Ax, is a graded ideal. Which makes Lx a graded algebra. Now the proof actually, that's the proof, okay, of these three things at least. There is a fifth proposition here, which we should go ahead and we can go ahead and write that out. Doesn't rely on anything. The homogeneous component of our graded algebra Lx of Lx1 so the first grade of Lx has a basis of x, and the homogeneous component Lx2 has a basis of elements x, y, written in this bracket. I don't know if that's the Lie bracket or not. Where x and y are of course in x, but also x is less than y for some total order on x. And while I haven't looked at the proof yet, I'm guessing that's just so we don't double count x, y, and yx. Alright, now let's look at the proof. For 1 through 4, so we're going to make these curly brackets be a little less confusing. We're going to let I that be the set of A in AX such that every homogeneous component A belongs to I, then I to this is an I guess let's write it in a less misleading way. I to that is a two-sided ideal, and is also in our original ideal I. So now we're going to let X be in our algebra AX as the sum of homogeneous components x to the n. Then x times x is equal to the sum of these xn squared plus the sum for essentially grade n less than grade m, xn xm plus xm xn. And keep in mind these are in I as their square of homogeneous components. And this is equal to xn plus xm squared minus xn squared minus xm squared, where all of these are in I, because I is generated by partially by elements of the form AA, and all we have essentially here as 4 parts all to form something squared. So we have here all of the homogeneous components here belong to I. So x times x as with I is in I to the thing. Now we let x be the sum of xn, y to the sum of yn, and z to be the sum of zn, such that, and that should be so would be better. So that the Jacobian of x, y, z is the sum of Jacobian of their every possible combination of their components. And this is of course going to be inside I prime, I sharp, so this whole thing is. Thus, I sharp is equal to I. Maybe this is a proof of just number 4. I think the first 3 are all pretty obvious. I mean, I don't know about the second one because I don't know what the terms are, but the rest are all just like what we've seen before. Aside from part number 4 and the proof of part number 5. What to keep in mind is that the first homogeneous component of Lx has basis x, and the second has basis of like x bracket y for x less than y. Okay. First off, we see x generates Lx, and the bracket of x with itself generates L2x, which is just the pairwise x and x for x left less than the right as above. Consider the module E, which is k to the x and the Lie algebra of the direct sum of E with the wedge product of 2 copies of E. This is equal to G. It says this was an example we've seen before, but I don't remember anything like this. But now's not the time to look. I'll look after here. The canonical map of x into G induces a Lie algebra homomorphism from Lx into G and the direct sum of Lx1 plus Lx2, which I guess is supposed to be the analogous of E and the wedge of 2 E's, going to be sent into Lx and into G, and this whole thing as one map is an isomorphism. So, I don't think we should start a new section yet. There's 2 things I want to look into. First off, what is this example they're referring to? Okay, first off, E, a few points of confusion for me I'm going to clear up. This E equals k to the x is the free module, the free k module with basis x. So I think that would just be a bunch of copies of k indexed by the elements of x. Which, as I suspected, makes our wedge of E with itself just kind of our current stand-in for the Lie bracket. And what was my other? I wanted to see what the example was. I wanted to see, we saw before if you remember from before, I mentioned briefly from this proposition that part 2 references a direct system. I don't know what a direct system is, so I'm going to look into it here real quick while I'm just like stalling. Okay, I'm going to write this out here because this is part of my studying and I need to write this out. A direct system. This is once again from a different source, so it's going to have different notation. For mi indexed by an indexing set I, which is a family, a collection of R modules indexed by a directed set. I don't know what that is. I'm gonna I think directed in this context just means ordered. And so sigma ij from mi to mj, with I being not above j, a R module homomorphism. Then the collection of mi and sigma ij is a direct system when sigma ii is the identity on mi for all I, and sigma ik is always just decomposed into sigma ij composed with sigma jk. I wrote those in the wrong order, but you get what I'm getting at. I'll double check a definition of a directed set, but I'm thinking it's just a set with a total ordering on it. Directed set is a set with a reflexive and transitive binary relation with every pair of elements having an upper bound. So it doesn't have to be totally ordered, but every pair of indices, there has to be an element that is bigger than or equal to both. Okay, so that makes sense. And then in our proposition, this is just saying, yeah, that it behaves with a directed set in the way that is kind of intuitive, the direct system, sorry. So essentially, if like, I think the first ones in the direct system are going to be like big and they're all going to close down into something. Maybe? No, that's not necessarily true, because they don't have to be surjective, but Yeah. Alright, well, I guess we'll call it here then. That's the first 3 sections of this chapter. And how many sections are there left to go? 5, so I'm thinking we might get through this chapter today. We also might not, because this is as long as the next one, so this will take 1 or 2 days. I don't know. That's not really important for you guys. You just watch them as they come out. But yeah.